This is the hydrography community call for USGS hydrography program. If you notice, we used to call this the advisory call. We've changed the name of it because there's some specific kind of legal things involved with what's called an advisory committee, and this is not one of those. So we wanted to change the name to make it clear that this is just our communication with the hydrography community, and not one of those special types of calls or special types of committees called an advisory committee. Today we're going to have a talk by John Nelson in the USGS, he's going to talk about bathymetry data and some of the recently collected bathymetry data that we've done as sort of a pilot project. We've done a few pilot projects collecting bathymetry data using LIDAR, and in conjunction with that, using ADCPs or sonar data, basically. So we're experimenting with this technology right now. We don't have a full-blown program like we do with the 3D elevation program, the 3D program, or the hydro program like NHD, but it's something that we're considering and trying to learn more about. We do have the ability to contract with private vendors to collect this kind of data through our GPSC contract. GPSC is, we call it the GPSC contract. And so it is something that we can do, but we don't have funding at the moment to do like matching funds or anything like that. So right now, we will go ahead and pass the mic over to John.
Thanks, Alan. So I'm Jonathan Nelson. I'm at the USGS Geomorphology and Sediment Transport Lab in Golden. And I'm going to talk to you today about some work we did to sort of illustrate how Bathy Lidar data sets can be used with computational modeling to answer a variety of issues. So this work was originally presented a few weeks ago as a short briefing to the Potomac River Commission. So I've added a couple of slides to it because I think some of our oil spill people are on today as well. But primarily, this is just going to be stepping through what the data looks like, what kind of modeling we can do, and it's sort of a tip of the iceberg view of what's possible with these detailed data sets. And the actual computations that I'm going to show primarily done by myself and Paul Kinzel in the same group, and we have many iRIC collaborators around the world. For those of you that aren't familiar with what iRIC is a sort of generic interface that was originally conceived in my group about 10 years ago to try to make surface water models and sediment transport models available to our users in the water science centers. Since then, it's developed and become not only a platform for USGS models, but it's now sort of a community platform that has on the order of 25 1, 2, and 3D models for rivers from scientists around the world. So although this started at the Geomorphology and Sediment Transport Lab, but it's bigger than that now. So I'm speaking to you today, not from the lab, but from my barn, lately repurposed as my office and the land of forgotten furniture. So I apologize for any crowing roosters in the background, but that's the state of my office situation as of now. So let's just go ahead and first look at what topo bathymetry data looks like. So this is just a simple map of the reach of the Potomac for which we flew topo Bathy Lidar. For those, I think probably most of you are familiar with the idea, but everyone knows how LIDAR works. You shoot a laser beam, you get reflected light back, and from the timing information, you can figure out elevations, that along with GPS and so forth. So The idea of bathymetric LIDAR is you use visible wavelength LIDAR that penetrates the water. It goes through the water, is reflected off the various things in the water column and also ideally off the bed. If the water is too deep, you don't get a reflection from the bed. And you have to, as Alan referred to earlier, you have to basically amalgamate different kinds of data sets. And so here we've got the Potomac, a couple hundred kilometers or something on that order. And just in detail, I'm showing you the Point of Rocks reach and a reach downstream that actually is significantly deeper and has, as you can see, voids in it where the LIDAR did not penetrate to the bed. This is a typical bathymetric LIDAR data set. So the idea would be that we would go in and either use existing data or go out and use acoustic devices to fill in that missing data. We're working on that now, but today I'm going to concentrate on this what I call the modeled reach at the Point of Rocks, which is about a 15-kilometer reach where essentially we've got a complete data set. So we've got bathymetry and topography here, and it's quite detailed. So this is the ideal situation. My group first did bathymetric and topographic LIDAR just about 20 years ago in collaboration with NASA when it was a little more experimental, but the same issues, arose back then that are still present now, having to do with the inability to penetrate to the bottom in certain situations and various other things. So it's not a panacea, but it does offer the capability for us to get good data sets in certain kinds of rivers in much less time and, well, depending on how you measure effort, perhaps less effort than would be required. For example, this reach, if you were doing acoustics and ground surveying and whatever other standard techniques, to do 15 kilometers of a reach of the Potomac at this level of detail would be a very significant undertaking, certainly weeks of work. So, and instead, this can be done in a relatively short amount of time, hours, maybe a couple days. And we've done this on 10 or 15 different rivers around the country over the years. And so we kind of know what the pros and cons are. So what I'm going to do is just sort of illustrate what that data gives us access to in terms of computational modeling. And I'm going to do it with iRIC. That's not necessarily the only tool out there, but it is a tool that we commonly use, and it has a lot of different kinds of solvers within it. So we can look at 1D or 2D or 3D solutions. We can do particle tracking for problems like the dispersion of contaminants. We can do sediment transport, morphologic evolution of the channel bed, and things like that. And I'm just going to show you a few examples. So the hierarchy of approaches for the Potomac I'm going to step through is I'm going to start with a quasi-steady 2D model called FastMech over that Point of Rocks reach at high spatial resolution. I'm going to then, from that, go to a fully unsteady model called Nice 2D Flood, which is, again, in iRIC, over the same reach with the July 2020 high flow, and then use that same model over a shorter reach with the 1936 flood of record. I'll show you some particle trackings at both low spatial resolution and time resolution and much higher spatial and time resolution. And I'll mix in some other examples just to illustrate methods and things like that. But this is not going to be a technical talk. It's really just an overview of the kinds of things we can do with data sets such as the one we collected here on the Potomac. So this is what the data looks like. That's about a 15-kilometer reach, and it consists of both depths in the channel, or elevations of the channel bed more accurately, and elevations of the adjacent land surfaces. So the nice thing about this is we get a seamless data set, and it's pretty easy to right away run a variety of different computational models to route both standard flows and also floods and even huge floods, because we have the land surface presumably to quite high elevation around the river. So stepping ahead, the typical first step in modeling this is we make a coordinate system. In iRIC, this is all done through user interaction just by drawing a center line down the river and expressing the resolution. This is actually being graphed at a much lower resolution than the actual model, and I'll zoom in and show you some higher resolution results. So with this coordinate system fit onto the data, we can run a variety of models and get water surface elevations and vertically averaged velocities from those computations. So this is just a single example of water surface elevation. This is done for the flow when the LiDAR was flown. And one of the things that many of you probably know is when you do a model of a river, you have to figure out what the roughness is. Sometimes that involves a lot of spatial accounting and sort of spatial mapping of different areas of vegetation, different substrate types, things like that. In this case, we're going to just use a single value of roughness and calibrate it using the LiDAR data. So the LiDAR gives us not only the bed elevation, but the water surface, essentially from the first return of the LiDAR. So we're going to use that to calibrate roughness for these model runs. So here we have a simple quasi-steady 2D run with water surface elevation that we've adjusted the roughness to try to give a good RMS fit to the laser measured water surface elevation. So here I've added the velocities onto that same plot, but that's really not part of the roughness calibration. So these are what the LiDAR returns look like for the surface, and these were developed from the LiDAR data by Paul Kinzel, just using a filtering algorithm that picks the first return off in the region of the river. It's not perfect, but it generally does pretty well. And sure enough, the water runs downhill, so that's a good sign. So we've got this water surface elevation. Now we can compare that to the model and iteratively adjust roughness to try to get the best fit. Again, this is a very simple sort of standard procedure when doing a model of this type. So when we compare water surface elevations from the model and the measurements, we get things that look like this. The measurements are shown as points. You can see there's a bridge about halfway through where we got reflections from the surface of the bridge. And the lines are actually the model result. And because there are results on, throughout the channel, and we're just picking the closest computational point and essentially filtering it onto the locations of the measured points and drawing lines between them, you get this sort of strange effect. But if we go to a more conventional view of the predicted and measured roughness, you get something like this, which is generally pretty good. I forget what the RMS value was, on the order of 10 or 15 centimeters, if you exclude the presence of the bridge, which gives obviously a quite large error, since we're measuring there not the water surface, but the elevation of the road. So this allows us to calibrate roughness, and then we can go on to more complicated modeling. Zooming in on that model, now I've zoomed in on the bridge we were just speaking about, we get results like this. You can see flow around this little upper channel in the floodplain and sort of typical flow. Now, this is not the resolution of the model. Excuse me. This is a much lower resolution depiction where we're just plotting, like I think it's every 10th vector or something like that in the flow solution. If we zoom in on this region downstream of the bridge, I hope you guys can see my mouse, but there's a region where there's a bunch of rocks and there's sort of a complicated flow around that. This is a rocky bed. It's got some interesting features. If we zoom in on that at full resolution, we can actually see that the flow is resolved. We get steering of the flow around these rocks, between the three rocks down here. So we have a very highly spatially resolved pattern of flow around even relatively small scale features. The reason we can do this is that this is a quasi-steady model. So to do this with an unsteady model would be computationally very challenging, but we have a quasi-steady model and the discharge is not varying rapidly. We can very easily and quickly computationally. I think this model takes like on the order of 10 minutes, 5 to 10 minutes to run at very, very high spatial resolution, because there is no Courant condition for those of you that are into computational fluid dynamics. So you can see we can get very high spatial resolution, but we can't handle rapidly varied flow. So that's the advantage of a quasi-steady approach. And this approach is, at this point, completely two-dimensional. I'll come back and show you some 3D results later on. So now we're going to look at a real hydrograph and go to an unsteady model. This is the flood from last year. I probably should have updated this because I think there actually was quite a large flood just a few weeks ago, but I'm too lazy. So there's just the discharge versus time back last year, and we'll run that through an unsteady model. And you'll see a telltale go along this discharge plot at the same time that you'll see the velocity vectors and contours, and presuming that I can animate this. There we go. Okay, so the flow is now about to come up, comes up rapidly. The river gets wider, obviously. The velocities get higher. No big surprises, kind of what you expect. You get more flow in these back floodplain channels, for example, but that's what a typical 15-kilometer river model looks like. So this is a fully unsteady model, so it does have the effects of the flow variation in it, the slope of the discharge, the slope of the discharge curve. And I should point out that quasi-steady models can actually be pushed pretty hard. You can have discharges that vary pretty quickly, not up to the dam break situation or anything like that, but the rule of thumb is as long as the slope of the floodplain is small compared to the slope of the river, a quasi-steady model is sufficient and computationally much faster. This kind of unsteady model, instead of taking a few minutes for this 15-kilometer reach, it has much lower spatial variability, but it takes on the order of over an hour, I think, for this longer reach, maybe a little less than that. So let's see here. Let's go on to the next slide. I'm going to show you some particle tracking results. I said this wouldn't be mathematical, but well, I lied. So, but the basic idea of particle tracking is very simple. If you have a passive tracer, you know its position, and you know the velocity of the flow, you can essentially project where that particle will be a little bit later. Now, in situations like groundwater where you don't have turbulence, particle tracking is super easy because it's purely advective. But all of you know that in surface water flows, water is turbulent, and so if you measure at a point, you get a variation about a mean. Our models typically compute that mean. Now, there are models in iRIC that are turbulence resolving. There are direct numerical simulations included, but really those models they're not really tractable for large river simulations like this. So typically what we do is we use what we call Reynolds average momentum equations in the models, and we average over the turbulence variability. Now, the problem with that is if you do that and you use that flow field to advect something, you lose the effect of turbulent dispersion. To bring that back in, you can assign a random walk characterized by the diffusivity from the computational model, whatever that computational model might be. So then the position of the particle is its old position, plus its advection by the flow, plus any active movement of the particle, for example, swimming if it's a fish, plus turbulent diffusion, which is just characterized by picking values randomly from a Gaussian distribution characterized by the diffusivity of the flow. So let's, here's a little depiction, and here I've used sort of a 1D, 2D sort of explanation where the particle moves forward, and we put 4 particles at this original red point, as they move downstream, they spread apart because of the action of turbulence, but that action of turbulence is governed by the correct turbulence diffusivity from the computational flow model. So we can look at both advection and dispersion, which for the people here interested in oil spills is, of course, a very important part of the problem. So I'm just going to show you a simple example. This is for a line source. This is actually the Delaware River. And what you get out of this kind of calculation is you get time of travel from the initial point of injection of whatever your tracer is. You get concentration at every point throughout the flow for all times during the concentration. So you get time series of concentration as well. You get spatial and temporal extent of whatever constituent you're looking at, whether it's a pollutant or something like larvae that you're trying to track through the river as part of a biological study. And you get spatial and temporal variability as well as trapping, and you have the opportunity, because you use a Lagrangian approach rather than an Eulerian one, to add behavior to those particles. I'm not going to talk about that, but what we are working now on having multiple populations and having interactions both between the particles and the flow and the opportunity to do geochemistry by having different particle populations actually interact using the USGS model FreakC. So this is an avenue of approach into a lot of different problems. So our line source, as it moves down the river, the particles in the middle or in the thalweg go a little faster than the edges. So this is sort of a typical 2D particle tracking. Many of you have seen results like this. Okay, so let's go forward. Yep, sorry. And then, one of the problems with this is that if you go to a complex reach like this one, this is on the Snake, what you find is that if you really want to understand the spatial distribution, not only in terms of concentration, but in terms of exposure time, that is things like how much time is this pollutant present at a given location, you need a lot of particles. And this is sort of the computationally challenging, challenging part of this problem. So in this plot, you've got particles moving through the reach, but you've also got the blue and orange showing you essentially the integrated particle counts in cells, or what you might call exposure. And you can see, even though most of, I'm having problems here, aren't I? You can see that even though most of those particles zip down the thalweg, a lot of them end up in eddies and hang around for a long time. So even though the highest concentrations are seeing in the thalweg, the actual highest exposures are in things like eddies. So if you're looking at water intakes or things like that, this is very important. This is what you want to know. How long does this stick around? How much is being sucked into my water intake and things like that? And the downside of that is you need a lot of particles, because so many of them flush through that to model these trapping zones, you need a lot of computational muscle. So to get around that, and I'm just going to show you a simple example, we developed an idea over the last about 18 months with new code that used what we call cloning and colligation. And cloning essentially allows the user to identify a region in the flow where they need very high resolution information. So it's easier to show this by example than to actually explain it. So here's just a simple flow calculation for an eddy in the Grand Canyon. And if we do a particle tracking simulation, you can see most of the particles go downstream. A few get into the eddy. Eddies aren't actually very well connected to the main flow, so a few get in and are slowly bled out. But in this case, and in many other cases, we're specifically interested in what's going on in these relatively low velocity trapping zones. And having 4 particles isn't really good enough to give us any spatial information. So what we do is we draw a polygon that identifies a cloning region. We can also do this with mathematical relationships specifying a minimum density and things like that, but let's start simple. So here we have a polygon where we say, if density is below a certain point, particles should clone, that is, they should split apart, each having half the information of the original particle. So for example, if this were a pollutant, each would represent half the amount of the original pollutant put into the river. Or we could make them split by 1/3, 1/5, 1/12, whatever we want. And we can continue that through many generations so that subsequent particles can split again, and we can get whatever degree of accuracy we want in the region of interest without having to calculate millions and millions of particles. So here's that same calculation now with cloning. You see particles going to eddy, but that's because that's within our polygon. They begin cloning, and you can see the generations quickly get up to 12th generation. We get very high detail in the specific region of the polygon we drew, including vortex shedding and all kinds of interesting fluid mechanics, but without having to supply millions and millions and millions of particles through the main channel. So that's the idea. And now I'll show you one more example where we have big differences in scale. We have rapid velocities in the channel and very low velocities in a floodplain pond, which only connects at the highest flow. So this is for the Kootenai River. The hydrograph is shown in the upper right. You can see water goes in first at the lower connection, then at the upper connection, at which time the pond fills and water starts going out the lower connection. So there's a lot going on, but the velocity in the channel is orders of magnitude, well, a couple of orders of magnitude higher than that in the pond. If we do particle tracking with cloning, instead of having to compute millions of particles to get any information in the pond, we can have a cloning polygon in the pond region and get, these are now moving at, like, in many cases, fractions of centimeters per second in the pond. It's a very slow process, but we do get the circulation in the pond. We can see the dynamics of when water comes in, first the upper channel, first the lower channel, then the upper channel, and then the lower channel reverses and so forth. So sorry, that probably went by a little quick. Let me back up. Well, I can't back up. I'm not sure why. Anyway, oh, I guess I can. It's laggy. I apologize. So go forward again. So let's, again, water begins to go in this lower channel into the pond. The pond is slowly filling during this period. As the pond gets flower, this is during a hydrograph, so the river is still coming up. Ultimately, water starts going in this upper channel, the pond fills further, and water then comes out this lower channel. So you can see water starting to go in here, then it gets over the sort of break in the topography, and then we've got this kind of circulation. And that's what's observed in the field as well. So let's go back to the Potomac and look at some particle tracking. First, just a simple sort of low spatial resolution, low temporal resolution particle track. And again, I started with a line source. It could have been anything. I can put in any source I want, wherever I want. So it moves down the river under the influence of the velocity field that's computed. It goes around islands, things like that, or bars. You know, we get a picture like that. So we're going to zoom in now and look with a little more detail at some of those points we looked at before. So here's that back bar channel that I showed before. And if we look at the particle tracking through there, first without cloning. So we get a few particles back in there. We don't get a whole lot of detail. But if we were specific, if, for example, there was a water intake in that back channel, or there was some industrial installation and we really wanted to know where things were going and where and how long they were going to stay there, we would use cloning. And whoopsie, sorry, there we go. So I'll make a cloning polygon as before and run this, and now we get a lot more detail. It's a little hard to see in this at this resolution, but we have 10 to 20 times the number of particles, and we can see more spatial resolution in that channel. So moving on, this is now the same reach of Potomac with a 480. This is the flood of record from 1936. Or I believe it's the flood of record. Yeah, it's at least the USGS flood of record. So again, we can look at this. We get flows much higher on the, you know, the particles are now moving over a wider range relative to the size of the channel. Of course, the channel is just a single depiction from Google Earth, and it wasn't taken at high flow. So we see what appears to be water and particles moving outside the channel. That's because there's water outside the photograph channel. All the outputs from iRIC, velocities, stresses, sediment fluxes, concentrations, everything are directly available in KML. There are tools to look at them within iRIC, but you can also bring them into any KML-based software like Google Earth, for example, or anything like that. So that's all I've done to make these plots. Okay, so now we're going to zoom in a little more, and we're going to look at that upstream bend. And here we have the time average flow developed by a quasi-steady model for that peak flow event. And you can see at high flows, that during this high flood, you actually get flow separation and an eddy near the point bar, or the inner side of this bend. So if we now look at particle tracking for this more highly resolved flow field, whoops, yeah, I think this is okay. First, without cloning, I'm sorry, it is with cloning. What you see is that you leave some particles behind when you clone, and those particles then move upstream in the eddy itself. So this is at a fairly crude temporal and spatial resolution. But now we're going to look at that same problem with a higher resolution. First, we're going to look at well, I guess that's something not quite right there, but let's skip that and we'll look at this flow field. So now we're going to look at a time varying flow field with a high frequency resolution. So instead of seeing a constant eddy like we see in the quasi-steady flow field, we're going to see a varying flow. Still, on the average, it looks like a lateral separation eddy, but there's vortex shedding along the outer margin of that eddy. And as any kayaker will tell you, and there's a lot going on at the edge of eddies. And so we'll now take that more highly resolved flow field and look at the movement of particles through that flow field. So now, again, we have a line source. This is a lot of particles, so it moves a little slow, but it will made a cloning polygon near the apex of the bend, and you can see cloning has already started to occur. And now you can see these big vortices. So on average, we have a single eddy, but what's really going on in terms of the physics of exchange is we get a lot of complex temporal and spatial structure that, for understanding certain problems, is critically important. So this sort of helps you to see, I hope, that there's a hierarchy of approaches of spatial and temporal resolution that give you, progressively more accurate views of the physics of what's going on in the river. So everything I've shown you so far has had particle sources, just simple sources upstream, but sources can be anywhere. And so I've just brought in one more example to illustrate that. This is during a measured flood on the Delaware, actually, and I've just put a pile of some neutrally buoyant material here, and we'll animate that. And what you'll see as water comes up behind it, as the water comes up, it pushes that material over in sort of a linear source, and over time it's pushed out to connection with the river and is then advected downstream. So you can have multiple sources, and you can do all kinds of things with sources, including to put them exactly where your spill occurs and get concentrations and spatial patterns from that point forward. Just wanted to illustrate that. So, I've shown you a lot of pretty pictures, and this is just a very short talk, so I haven't gone into a lot of detail, but we have done dye studies. The black here is for 3 different positions. These were done a few years ago on the Kootenai using a simpler version of the particle tracking model. The black lines are the predictions of the model. The dotted lines are measured concentrations from sondes. This is a rhodamine experiment, and this is at 3 different locations down the river. So these are explicit spatial locations. They're not cross-sectionally average or anything like that. You can see it's not perfect, but generally we're doing a really good job of capturing both the spatial variation as the peak drops and getting the concentration at a specific point. Correct. That's not so easy. Getting the cross-sectionally average concentration point at cross-sectionally averaged concentration correct is quite easy. Getting it right at a point means you've got the distribution of the movement of that material in a 2D sense correct. And the dark shaded area is showing you what the variability is across the cross-section, because we had several sondes. But so again, it's clear that we fit this individual sonde, which was buoyed in the river, quite well using this kind of approach. Now I'm going to step to a slightly different viewpoint. So far, everything we've talked about has been just single calculations in a decoupled mode. But so done flow calculations, and then subsequent to that have calculated the movement of material. And we can do that in an Eulerian sense too, just conventional advection diffusion equations. But there are situations where we need to consider what goes on a time step basis. And there are also situations where we want to have a coarse view of the entire system, but we want a very high resolution depiction of what's going on at some specific location. I've showed you how cloning can give that to some extent, but about 2 years ago, maybe 2.5 years ago, we were working on trying to figure out how to do what we call multi-grid. So not multi-physics, but multi-grid calculations, where we could have coarse grids coupled to fine grids, and also 1D grids coupled to 2D grids, and 2D grids coupled to 3D grids within iRIC. At the same time, Don Klein came to the USGS and started saying he wanted us to work on coupling models. And we took a step back and we realized that by taking a more general view, we could make models coupled not only for multi-grid and multi-dimensionality, but for in a much more general sense. And so these are relatively new developments. So I'm just going to show you a couple examples. I'm almost finished here, but this is a rainfall runoff model running on the same on a 15-minute time step with measured rainfall, actually partially measured, partially interpolated using with Doppler data. And this is the river in this basin. So I'm just going to animate this. We're going to see rainfall on the left, and we're going to see the flow field on the right. And these are coupled at the time step basis. And so within the iRIC interface, you set up these models separately using an interface, so there's no programming involved, and then you run them, and using MPI with server software, we manage both processes, and we run both processes together. But that same general approach can be used across any kind of physics, including habitat models, fish swimming models, anything you can come up with that's written in Fortran, C++, or Python. You can couple together within the iRIC, it's called iRIC-MI framework, in order to have this coupled model capability. So we should see rainfall on the left, and you'll see there's a lag, but the flow comes up in the river as this is running. So this is a very simple example of coupled models within the iRIC-MI system. Now you could have subsidiary couplings. You can couple as many things as you want, and you can have disparate time steps. So I could, for example, have a habitat model running at the same time with a bioenergetics model for fish running at the same time, things like that, all within the same computational framework. So let's go to a little more complicated situation. Again, rainfall runoff coupled to a 2D unsteady model, but now it's more realistic. We've got something like 10 tributary basins. We're running 10 rainfall runoff simulations and 1 river model. So you can see the inputs coming down from the separate channels. And this is an area where we have detailed bathymetry again. And you can see the blue dashed lines. Those are actually lines that were digitized as the maximum extent of flooding in this urban area. So this is an urban flooding model driven entirely by rainfall with a river model, all coupled together, running on the same time step. So I'm going to zoom in and show you that inundation as predicted from this approach. The only input is topography, the river roughness, and the rainfall. So you see we do a pretty good job of getting maximum inundation. We have 2 ways of handling buildings. You can explicitly put them in using Google Street Map or digitization, or you can treat them as porosity in areas that are too complicated to resolve. You can give a building porosity and use that to do models like this. So this is obviously, this is a very large flood, and the city was, completely inundated, but the model did a good job of hindcasting that. The important thing to note is this kind of process can be done in a forecasting sense using rainfall from, for example, the National Water Model or any other approach, and predicting what's going to happen both within the river and, more importantly, in this case, on the floodplain. So stepping to just very quickly 3D results. In a 3D model, you've got vertical shear in the primary flow, and you've got all kinds of things going on in the what we call secondary flow with different directions over the depth because of curvature or bathymetrically driven calculations. I'm not going to go through this in great detail, but we can do those too, and then do tracking, for example, near the bed or near the surface. This is this calculation was done. It's the upper Kootenai. There was a spill of diesel oil from a train that derailed and went into the Kootenai upstream of Bonners Ferry on New Year's Day, late on New Year's Day of last year, and I did these calculations in support of that. So this just shows where surface material is going, and also more importantly, where it sticks, where it hangs out over this hydrograph. And you can see that you get a lot of material along here, and that was well supported by observations in the field. Finally, you can go nuts, add all kinds of things together. This is just a simulation of Hurricane Harvey. And so there's the storm track. Again, this is hindcasting. This work was done by Yasuhiro Ishida, a PhD student that finished recently working for our group. And so it's going to see the storm surge comes in as a boundary condition. We're going to kind of jump around and look at all the iRIC model results for that situation. Again, we can go from large-scale river stuff to individual urban area inundations through this process. This isn't a particularly high-resolution model, but it's running obviously over a very large area, essentially the greater Houston area, showing both inundation and river flow. And again, the inputs are the sea levels and the rainfall only, and a very good bathymetric topographic depiction. So you get the idea. And then just in closing, it's pretty easy to take these kind of results and generate them into things that you can look at on, for example, a cell phone, to see what water inundation looks like in an urban setting on the buildings. So that's sort of a whirlwind introduction to what high resolution bathymetry and urban area digitization can do for our capabilities in making predictions. I would be happy to answer any questions anyone has or whatever. So I'm done. Thanks.
Yeah, great. Thanks, John. This has really been fantastic. I'm hearing an echo, but if people have questions for John, you can unmute yourself and ask, or you could just type your question into the chat. We have a few minutes here, so please ask if you have any questions.
Oh, it looks like there's a message. I've been in conferences.
If you don't have a question, I ask that you mute yourself. Yeah. I was gonna post. I'll post another link in here to the chat, and this is an inventory of bathymetric and topobathymetric surveys that have been done. It's probably not exhaustive, but it's sort of the best list we have so far. And a little earlier, I put in the chat a link to sort of our first complete topobathymetric terrain model for an inland river, which is on the Kootenai River up in North Idaho. So there's a link to that there. So that's where they've taken, bathymetric data like what John has been showing, integrated it with land surface from terrestrial LiDAR, and produced a single surface of the land, including down under the water. And that would be, I think, ideal, right, John, for doing this kind of modeling. We've been experimenting. We've done a few pilot projects on that sort of work, and I can show you here how you can find some of that data. Not all of it has been published yet. But do people have questions for John first? Let's see. Lots of wows. And
This is Cynthia. Can you hear me?
yeah, we can, Cynthia.
I'm sorry, I don't have a question for John so much, but this would be a good place for me to insert regarding the inland Bathy inventory. The original one was developed and put on ScienceBase as a data release product. So the inventory is good through 2020 surveys collected, but the footprints and map packages, frankly, were my first attempt at trying to take all kinds of data and put it into one format. So they're pretty wonky, so I apologize, but new footprints are being developed and hopefully will be out in another month or so. So if you look at the map packages, the footprints do give you a good idea of location and extent of survey, but many of them do not really show, the shapefile don't show the boundary of the actual survey. Just so that people know that and aren't shocked if they look at the map packages and wonder what they're looking at.
Okay. And also, I think you mentioned earlier to me, Cynthia, that you're planning an update to that.
Right, and that's
inventory?
I'm doing right. And the 2020 inventory is going to stay as is, but the footprints are in really sad shape because, like I said, it was my first attempt. So I'm redoing all those. But right now, what's in the inventory is good through surveys collected through 2020. There's 75 or so more to add, but I wanted to get the map packages cleaned up before I go and add those on top of what's already there. But they are surveys collected from the first ones discovered up through 2020 USGS inland to coastal zone surveys. So it's pretty exhaustive, I hope. It's what could be found.
Yeah, that's great. That's great to have that information. I'm sharing my screen right now. Are you seeing it? It's got the National Map Viewer on there. I wanted to show people where they could find data similar to what John was showing. It's not a lot of places yet, but we do have a number of places where we have this kind of information, this topobathymetric data. And just to show you how I got this, there's this layer list on the National Map Viewer. And I'll put a link to the viewer in the chat here in a second. And you have to go in and find the list scroll down to the 3-depth elevation index, turn off these other things, and just turn on the topobathymetric data index. That way you'll see these areas, and there's been quite a bit of work done in some coastal areas on integrating the terrain and the bathymetry together for coastal models. Those go a ways inland as well. So there's those, and I know there's a new one being developed in the northern Gulf of Mexico, and I just saw recently there was one developed along the southeast coast here in the Carolinas and Georgia coast. So there's quite a bit of that along the coast. And then there are these few inland areas where we've done the Klamath River, the Kootenai River, part of the Colorado, and I think this is the Niobrara in Nebraska. So, and then there's, I don't even think the Potomac and the Delaware are showing up here. They may be obscured. But you can also, if you click on this, if you turn this query layer on under the DEM, the 3-depth elevation index, and turn off all of the other layers and just leave these last three checked, then you can click on these and you can see, for example, here's, this tells us about that Klamath River bathymetry data set. And it's got the bathymetric, it says this is a bathymetric-lidar data set. And you can actually get a link to go actually download it. And there's some other records there with some additional other, you know, there's that was the bathymetry. This is a topobathymetric lidar. And then I think maybe some other data sets there too. So anyway, just to let you know how to find this kind of data that we have right now. And I'll just mention again, like I said earlier, we don't have a program yet to develop or collect this kind of data everywhere, but we're talking about it, and we're actually hopeful that we'll be able to push that forward and actually collect this kind of data on a much more routine basis, something like what's been done with the 3DEP program. And that hopefully that's in the future.
Al?
Yeah.
This is Jim Mitchell. I'm just wondering, everybody loves, you know, out-of-the-box data. For these 3D applications, you're going to need to have everybody on the same sort of datum. And I'm wondering how you get, you know, datum corrected, gauge heights and water levels, that kind of stuff.
Yes, that's obviously critical for doing this kind of work. I didn't see whether we have, is Jeff Danielson on the call?
No, he's not.
Yeah, he's our expert in doing that stuff. He works at the Aeros Data Center. He would be the best person to answer your specific question about that, Jim. But it's definitely something that you have to consider.
Yeah, there's a new datum coming out in 22. I guess it'll be released in 24. Seems to me like we have an opportunity to get everything on the same dang datum now, and we ought to do it.
Yes.
Yeah, and that datum shifts as time goes on too, right? So it's not going to be. Yeah, exactly.
Thanks.
Yeah, good question. Definitely something that has to be taken into account here. Was there anything further? I didn't see.
Matt Mercurio had a question up earlier, and he says, cool AR on the phone. Any more info on that? I guess that's for John.
I'm sorry, I didn't understand the question. AR?
I guess it's the augmented reality on the phone. That stuff you showed on the phone. He says, do you have any more information on that?
Yeah, it's basically those graphics images are developed right out of iRIC. So it's part of the graphics package. Putting them on the cell phone like that is, once you have an image, is pretty straightforward. But I have to admit, in that slide, that was done just by putting the image on over a cell phone frame, if you see what I mean. So there's no fancy AR software involved. The realizations are 3D within iRIC, and then so we're just drawing the surface essentially within Google Maps, or excuse me, Google Street Map, to get those images. Does that make sense? I'll assume it does, unless someone sends me another question.
To me, it does.
Okay.
That's Matt's question. Yeah.
I noticed that someone asked about, why do we need river bathymetry? And that's a really good question. And the problem is that in gigantic floods where the conveyance in the channel is a tiny fraction of the total amount of water going out on the land surface, bathymetry is not very important. But there's a whole lot of floods in between normal river flows and those sort of Noah's flood events where knowing the conveyance in the channel and knowing where water comes out of the channel is extremely important for understanding flooding, and especially urban flooding, because unfortunately rivers don't just sort of overflow their banks and move out a lot sort of rectilinear onto the floodplain like we like to think. I mean, they come out as channels and crevasse splays, and they shoot water like a fire hose onto the floodplain. So knowing the details of the bathymetry in the channel, I would say for all but the very largest floods is really critically important for making good predictions.
John, we're getting short on time, but I'm able to stay longer if you are. There are some more questions that have shown up in the chat. One is basically, can outside scientists or groups access and use your software, modeling software, the iRIC software, I think is
Yes,
what that
absolutely.
about.
It's all in the public domain. It's available at i-ric.org. It's all free. There's 20 some solvers. They all have tutorials. There's a developer's manual. And one of the things I like to emphasize, you know, we've taught like 150 classes over the last 8 years, but you know, you can people learn this from the tutorials on the website all the time, all over the world. And there's also a developer's guide showing you how to put your own solver into iRIC. So this is not a static piece of software that USGS puts out as something that's not changing. It's changing all the time. People are putting new solvers in and making them available. It's a community effort. We welcome other people. There is a developer's guide that in explicit detail tells you how to put your own solver into iRIC, and it's quite straightforward. The models are really decoupled from the interface itself. They're just introduced to the interface through XML, which is just a markup language that tells the interface how to interact with the model, what parameters are needed, and what tools are needed graphically to build coordinate systems and things like that. We have something like 20 coordinate systems, both structured and unstructured. So, you know, but by all means, if you have a different coordinate system, come on down. You know, we'll put it in there for you. And again, we welcome any collaborators to build this out for everyone to use. It's widely used, especially in Asia, because everybody lives on the floodplain and rivers are just generally thought to be more important. But it is used around the world, and we have lots of collaborators. Again, we welcome anyone else to join us.
Yeah, along those lines, could you explain the overlap and differences between iRIC and HEC-RAS?
So iRIC was originally conceived to support morphodynamic models, and it has since evolved to do a lot of other things. But one of the things that we still do is we predict with both 1, 2, and 3D models how the bed changes over time with most of the models in iRIC. So we have sediment transport, both bed load and suspended load, and we use that to modify the bed over a hydrograph to predict deposition on the floodplain, for example. And generally, we're strongly 2D, 3D, more on the hydrodynamic side. We believe HEC-RAS does a great job for 1D models. So really, we haven't put much effort into that. We're trying to complement what the Army Corps has done with a more 2D and 3D approach, including turbulence resolved models. There are models in iRIC. You can start with a flat bed and have a turbulence resolved DNS model and predict the formation of very complex bed forms that are extremely realistic. So this is really a state-of-the-art tool for bed change, as well as just a tool for what I've shown you today. In fact, really what I've shown you today was not the original center focus of the iRIC work. It was really about morphologic evolution, and to some degree still is, although we do have a lot of other tools. We have one simple groundwater model, and I'm working with Chris Langevin to incorporate at least ModFlow 6, especially because we want to use it in some of our coupled models to look at bank erosion. We do have some bank erosion now, but we want a dynamic groundwater problem coupled to the river problem because we believe it's important in a lot of cases.
Okay, great. Well, we are a couple minutes over, and I don't see any more real burning questions in the chat. So I think we'll wrap it up for today. John, I really want to thank you for the presentation. I think this has really opened my eyes to all the possibilities that are out there for working with data like the bathymetry data that we've been talking about. So really appreciate your taking the time to show us this, and we'll try and keep in touch and see how things develop.
Yeah, my pleasure on the presentation, and I can't really emphasize enough how important the bathymetric effort is to guiding future development, especially for real societal problems like urban flooding and dispersal of contaminants, things like that. I mean, having good topography is the key to accurate prediction. There is no question about it. So I hope that over the next decade or two, we move away from a sort of river averaged approach or cross-sectionally averaged approach to a more spatially explicit one. And I think the new techniques give us the opportunity to do that. So I'm excited about what you guys are doing.
Excellent. Oh, thanks again. We'll call it a day for now.